Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.
Good afternoon and welcome to today's Vision Systems Design webinar titled, How is AI-powered technology changing the smart city? Sponsored by Enclustra. I'm Linda Wilson, Editor-in-Chief of Vision Systems Design, which is part of Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit it to the questions window, and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Vision Systems Design website within the next 24 hours. You'll be notified by email when the archive is available. Now, I'd like to introduce our speakers for today's discussion. First, we have Gael Paul, who is VP of Innovation at Enclustra, a leader in FPGA-based systems on module technology. He leads a multinational team focused on developing cutting-edge hardware, software, RF, mechanical, and thermal solutions. With 25 years of experience in semiconductors, electronic design, automation, and cloud technologies, Gael is a recognized expert in product architecture, chip design, and field experience. Next, we have David Wyatt. With 30 years of experience in automation, David is a certified AIA Advanced Vision Professional and a charter member of the Machine Vision Association of the Society of Manufacturing Engineers. He also is founder of Automation Doctor. Welcome, gentlemen. I'll start with our first question. Smart cities have been discussed since the 1990s, taking shape in the 2010s and evolving rapidly ever since. To help ground us and our viewers, can you walk us through how a smart city operates today with AI and what key components are driving this evolution? Gael, let's start with you.
Yes, thank you. Well, welcome everyone on this webinar. Thanks for joining. I'm very happy to be with you, Linda and David, for this section. So what is a smart city? Well, it's a number of functions, and I will give you just a few of them. Surveillance systems for real-time video processing and rapid threat detection. It can be traffic management to optimize the flow of vehicles and reduce congestion. Environmental monitoring, gas or noise, for example. Smart lighting, adaptive lighting to adapt to the conditions in the city and the day. Energy, waste management is also very interesting, how you can optimize waste collection. Water management, smart parking, public transport, healthcare, and even all the way down to citizen engagement. Interestingly, Linda, a smart city pretty much operates like a high-end industrial facility with a multitude of sensors, multiple systems. Many of them are critical in terms of flows of people or information, and as well as security and safety.
David, how about you?
Well, thank you, Linda, Vision System Design, Enclustra, and Gael for inviting me along, and it's a privilege to be here. Gael really hit all the high points there, so I think that he's exactly right on when he talks about what the smart city is envisioned to be. You know, years ago, we used to think that it was flying cars and robots in your apartments helping you clean. And that's really not what it's all about. Smart cities want to enhance safety. They want to enhance sustainability, the quality of life, and the residential experience, the experience of the actual residents of their city. And they have to find a way to avoid some risks, such as data privacy. There's critical infrastructure security that they have to be aware of, and that adds challenge to the governments and public bodies that try to govern and contain those problems. Over the next 5 years, I'm expecting generative AI to impact cities through integration of digital government services, smart transportation, and interactive digital twins, where you have a city that you have modeled as a digital twin, and things that you want to do can be tried in the cybersphere, as opposed to maybe making some mistakes and building some things that don't belong in certain places. Without equality in mind, digital government could also risk replicating or exacerbating some existing inequalities. So we must be ensuring that our technologies and our innovations are deployed ethically and inclusively.
Okay, well, you've touched on some of this already, David, but let me ask both of you, what do you see as the biggest tech challenges in urban development? Like handling massive data, ensuring cybersecurity, and scaling up for growing cities. Gael, do you want to touch on this?
Sure. Well, what we've described a number of use cases, right? And what is interesting in those use cases is they actually involve sensing a lot of different stuff, comprehending the world in a way that wasn't accessible to us. And by the way, then processing that understanding, especially with AI. So the first challenge is the diversity of sensing for comprehension of the world. Obviously, vision, camera-based vision enhanced with AI is the basis of most of the systems. We now have the ability to make a lot of sense from vision-based cameras, thanks to AI. But that's not it. There's a multitude of other sensors that are very useful. I could cite image sensors, even all the way to thermal and infrared, spatial sensors, lidars, radars, GPS, physical sensors, pressure sensors, inertial sensors, light sensors, audio sensors, I will actually talk about that, or even chemical sensors. And let me give you an example. I think it's the city of Copenhagen that actually enhanced their water distribution system with a leakage detection mechanism. And that's quite hard. If you have buried pipes in the ground, how do you detect leakage? And one of the solutions found was audio processing. It turns out that if you listen to the sound of water, turbulent sound within a pipe, it can be detected when there's a leakage because that turbulences will be different. I don't believe my brain can figure that out, but AI can make a difference between a leaked and a non-leaked pipe thanks to audio processing. So a key challenge here is having the ability to aggregate tons of data coming from a multitude of sensors in real time. Most of the systems need to respond in real time. So that's the very first challenge. And maybe David, you want to tell us a little more about your perspective on that very first challenge.
Thank you, Gael. Yes, you're exactly right. The biggest challenge is going to be to put in the data infrastructure, because as you point out, there are lots of sensors, there's lots of data. You have to have infrastructure to connect all those things, and they're not all going to connect with Wi-Fi. Because although 5G is barreling in and we have a lot of bandwidth, it's going to get eaten pretty quickly. So we want to be careful not to pollute the airwaves because Wi-Fi is just radio, you know. So there's going to be a lot of infrastructure that's going to have fiber. They're going to have some hard wiring. And, you know, FPGAs are perfectly suited to this job, to reduce the data down to schemes that AI and generative AI can actually work with. FPGAs have been doing it since the 1980s, and I think they're kind of like the sister behind the other sister. You know, you don't see her a lot, but she's there, and she's providing the support that is needed for the CPUs and the GPUs. Many cities are focused on transportation, and they're looking for ways to reduce barriers to civic participation, promote transparency of that data, and improve access. We are going to see a lot of digital government services and smart transportation. Then we're going to find that through our interactive digital twins. And those digital twins are not going to be able to function unless we have the data stream coming in. And as Gael points out, there are LiDAR, there's radar, there are so many different things that we have to look at that is going to be our technical challenge. And what I talked about before was more of an ethical challenge. This is the technical challenge side, is getting that data reduced and getting that infrastructure for the data stream.
And in fact, Linda, let me augment the challenges. So we talked about the very first challenge, which is this aggregation of sensing data. It's usually called sensor fusion. But there's actually 5 additional challenges, right? The second one would be that the fast pace of changing models, AI models tend to change very quickly, or security threats tend to change very quickly. So the ability to quickly adapt at the hardware and the software level to the fast pace of changes. The third challenge is real time, which really calls for very low latency systems. In many of the situations, if you do traffic management or many of those, you need very, very low latency response time to efficiently manage the system. The fourth challenge will be low power. As you are putting down thousands, tens of thousands, hundreds of thousands of sensors and devices, they have to be low power. Otherwise, we would consume more energy than we would save to the smartness of our cities. The fifth challenge will be security, especially at the device level. Those are exposed, so we need built-in hardware-based security. And last is the product life cycles. As you deploy the systems throughout the city, you won't be able to change them every 6 months or every year. So you need products which have a very long life cycles, typically 7 to 10 years. So these are the 6 challenges that I could identify in the smart city development.
Okay, thanks. Well, let's dive into how tech solutions like AI-powered FPGAs are helping cities tackle major urban challenges. How are they making a difference? David, do you want to start us off with this one?
Sure. So maybe echoing this, but many cities are focused on the transportation-related use cases. And as Gael points out, those are oftentimes camera-related, although there are a lot of other sensors involved there also. They're looking for optimization. They're looking for intelligent intersections and multimodal transportation network improvements. Some cities recently, in some of the reports I've read, have taken a step back from large-scale deployments in favor of building their connectivity infrastructure first, which, as Gael points out, all of the sensors have to be, the data has to be collected and reduced so that they can actually use the FPGAs and the generative AI to make decisions. Pointing out, though, that the FPGAs are often at the device level, which I think is an outstanding place to put them. But they want to ensure the longevity of their initiatives. And so A city will focus on topics like sustainability and enhancements, and then work backwards to determine those technologies that can help them achieve those outcomes. Many deployments begin small scale in a block-to-block area, and then they determine that works. And like anything in the industrial world, you pilot it first. And I think that's where we are. We're in the pilot stage. In a lot of cases, I think we made some big steps early, and now we're piloting a lot of the new things. And this can grow, and this is sustainable. The FPGA can be rewired with software. It is replicating an ASIC, and so it is basically programmable hardware.
Thanks, David. And yes, in fact, Linda, let me dive a little more on that. But first, let us back up a little bit, right? There are essentially three classes of compute devices that can be used: CPUs, GPUs, and FPGAs. And let me go through them, because FPGAs aren't the answer to every problem. In fact, the simplest and most efficient, most easiest ways to do things would be a CPU. It's a very versatile device. It does sequential processing, and it's the simplest to program and the ubiquitous. And if the job can be done with a simple CPU, this is what everybody should do. However, CPUs tend to have high latency. They're very inefficient machines, so the power consumption for the task is not that good. And so they usually fall short on the number of activities. So the next level up would be GPUs, right? Now you're into data parallelism, single instruction, multiple data, model of compute, highly performant, moderate latency, very, very high power, extremely powerful, but high power consumption. And there you need a next level of programming, typically CUDA for NVIDIA GPUs. And they deliver great performance, but not usually at the device level. And then come FPGAs. FPGAs are massively parallel devices, millions of operations simultaneously, concurrent hardware. This is low-level devices, extremely high performance. This is spatial compute at its best. And they provide the best latency, as well, the lowest latency, as well as the lowest power consumption per task. They're extremely customizable, and you can do very, very complex processing. However, there's no free lunch. They're much more difficult to program than GPUs, which are themselves much more difficult to program than CPUs. They require expert level engineering skills to do that. So they provide a very, very high value than at the cost of a higher development cost initially. So FPGAs shine when you need low latency, low power, and combining, in fact, the sensor fusion, which is the sensing part of the task, with the thinking part, which is going to be the AI inferencing, and the reacting part, which is going to be, hey, this is the control action on actuators and others that I will do to respond to what I've measured. The second element to mention is that smart cities, like everything else, is a layered architecture. And there are really three levels in which this is being resolved. The first level is the device level. Think about cameras, sensors, distributed throughout the city. And here we're talking about hundreds of thousands of devices throughout, scattered. And that's going to give you a space where you have millisecond time reaction time, where you need low power. Obviously, you have such a high volumes. You need low cost of devices. The next level up is going to be the edge. Think about a control room that's going to be aggregating video feeds from tens of cameras, let's say in a mall, radius of maybe a mile. And there you have a bigger power budget, lower volume, and a moderate cost budget. And then finally, you've got the cloud level. And by the way, the edge is going to give you second time reaction. And then the cloud, this is the, maybe tens or hundreds of miles away from the city. It has minutes time reaction, extremely high compute power, and cost is less of an issue here. And so it's this overall combination. Now, FPGAs can actually play a role in all those three. They are very low cost, efficient FPGAs for devices, medium range FPGAs for edge, and high-end FPGAs for the cloud that will sit together with high-end CPUs and high-end GPUs from NVIDIA's and the like, AMD and the likes.
Nice. Hey, Gael, quick question. So historically, back years ago, one of the Achilles heels of the FPGA was typically when you put it into a system, you're going to be increasing the number of power supplies in your system. You have one for the memory, you have one for the CPU, one for the GPU, and then you have one for the FPGA. Next thing you know, you got 5 or 6 different power supplies in your system. What have you guys done to address that? I'm sure it's not still the case.
Well, you're right on the money, David. You know, as I said, FPGAs are no free lunch. They're very complex chip to put down, and there's an whole ecosystem. You mentioned power, but you could mention clocking and memory and connectivity. And what Enclustra, you know, the game of Enclustra is actually to resolve that for customers by designing a manufacturing system on modules. This is the single board computer approach. It's a complete subsystem delivered as a very, very small PCB. The smallest of our PCB is 30 by 30 millimeter, and it can be up to 60 by 80 millimeters, where the complete solution around the FPGA is already designed, manufactured, ready to go. And it really makes FPGAs like a software-defined platform, which is exactly what you get from NVIDIA or the CPUs today. So it puts them on par, really speaking, to that by solving all this plumbing, electrical issues, power, clocking, storage, memory, connectivity, once and for all, so that, you know, people listening to us today can immediately get to their unique differentiating value, your secret sauce. Add the stuff that you're really good at, that is going to make your product better and different than competition. Don't worry about power, clocking, and all. We've got it covered for you.
Sounds like you did a great job.
We're proud of that. You know, it's maybe less glamorous than doing, you know, the processing intelligence into it, but everyone has a purpose, right? And we're very proud that we've been serving over 2,000 customers and delivering great value for the last 20 years, allowing people to reduce risk and providing faster time to market.
It's interesting. Looking to the future, how do you think AI-powered FPGAs could help cities manage the massive amounts of data they're dealing with, especially when keeping things efficient and secure? David?
Well, luckily, technology is keeping up with AI solutions. The market's driving it, and it's a $31 billion market in the next few years. It's amazing. But, you know, just as an example, right now I can buy a 4 terabyte memory stick for under $100. And there was a day when we couldn't get more than 256K in the same box, you know. So to see what we are doing now with the technology advancements, and to see what companies such as Enclustra is doing, to see what NVIDIA is doing with their SoC modules, and the price points that are happening. And an FPGA can, in fact, live with the NVIDIA Jetson platform. There's several examples of that, and I think Enclustra is one of them. But the point is that we are able to bring forth the technology changes that we need to keep up. So I'm not punting into the future, but I'm confident the future will keep up as it always has. That's never going to be the problem. And I think we need to be relying on our youngest scientists to continue the trend of data reduction. Those guys are the ones who are going to be coming up with the next set of algorithms. If you look at just what H.265 has done to compression of video, everybody uses it on their Netflix, but nobody really appreciates it. And if you look at that compression and the people who came up with that algorithm, and it was based on the old run length encoding, but they did that in a color space. And I'm just really amazed when I read the data on how that came about from, you know, H.264, for instance, and then back to the MPEG carriers. And then, of course, there's new connection technology like GMSL, the Gigabit Media Serial Link, which doesn't go as far as co-express, and it certainly is not going to go as far as fiber. But, you know, in a local situation, you can have one piece of coax that carries both audio and video into an MPEG type carrier in software. And these are the things that are coming forward right now. We're at GMSL 3 now. And the bandwidths are getting bigger and the speeds are getting faster, which means we can have either more cameras or we can have bigger cameras to get that detail that I know Gael is really looking for. So, you know, we need the kids to pick up the Raspberry Pi. All right, the Raspberry Pi is not an FPGA. It's an ARM computer, but people need to start learning those languages. They need to start learning Linux. They need to start learning TensorFlow. They need to start learning PyTorch. They need to start learning Python, and not to mention C++ and Visual Studio. And until they get that experience, they're going to be handicapped. And so I'm really looking in the future for people that are going to come along and be able to do that with less and less hardware, and hardware like the SoCs that Gael points out, and hardware that's a lot cheaper.
Yeah, in fact, David, that's so great. You know, I've been around the FPGA industry for 20 years, and the evolution has been amazing. I would call it maybe, you know, the FPGA 3.0, and we keep calling them FPGAs, but they're much more than that. They're actually complete platforms. So they started being with the DNA of FPGAs was, you know, lots of IOs and hardware processing. And today you have terabytes per second of IO capacity in FPGAs. Then next wave, the second wave was SoC. So now for many years now, in those platforms, you have multi-core ARM subsystem with real-time processing unit, application processing unit, multiple ARM cores. I think the latest and greatest have up to 18 different ARM cores in these complete memory subsystem and very advanced connectivity. And the third wave is where you add AI processing into the mix. So that's now the plurality of the three all together into one chip. And there you've got AMD with the Versal technologies, who actually really have three pieces of silicon glued together for the SoC, for the AI, and for the programmable logic and IO capabilities. And you also have our friends from Altera who have infused AIs. They actually completely fused the AI capacity with the programmable logic. And both approaches are extremely good and high performance. So view them as platforms that can do it all for you. And they've been designed to be software definable. All these guys from AMD, Altera, and others, they give you tool flow where you can compile your train model that you probably trained on GPU somewhere in the cloud, and you can compile and optimize them for the target silicon and have them running at high performance. So they're natively going to read your PyTorch model and others, TensorFlow models, and deliver great performance. Likewise, you have all the compile chain and all the software tools to do your SoC, and obviously the tool flow for doing the programmable logic. So those platforms are phenomenal because they combine all three parts into one chip with lots of software environment and, by the way, an ecosystem of solution providers around it to help you not reinvent the wheel and get on quickly with your design. So the evolution is just...
You're running a multinational team, and it's mind-boggling the knowledge that you have to assimilate into one spot to be able to play in all those arenas at the same time.
Indeed, David, it's very right. The second aspect to your question, Linda, was security, which is really, really important. And we briefly touched on it previously. If you think, especially the device level, those devices are scattered throughout the city, in your example. They're not physically protected in many cases. They can be accessed relatively easily. A camera, as you can imagine, or even if you have street cabinets, they're not that hard. These are not vaults or Fort Knox vaults. So you need the highest security elements, and FPGAs provide hardware-based security. They're really what's so-called the root of trust, the hardware root of trust. And the programmable logic part is essentially a black box. There's nothing you can do, or virtually nothing you can do to figure out what's going on. Can you hack or spy on the FPGA part? It's virtually extremely hard to do that. So they provide best-in-class security, which is essential, especially at the device level, combined with the flexibility of software for AI and SoC.
Okay. Next question. As cities push for better energy efficiency, stronger cybersecurity, which we've touched on, and resilience against electromagnetic interference, how could FPGAs make that happen? Gael, do you want to start us off?
Yes, well, absolutely. So I already touched on security, but let me reinforce that. So hardware root of trust and hardware security is best in class. And this is what FPGAs natively provide. And they provide all sorts of different protection mechanisms against side attacks and cloning and whatnot. There's been a tremendous evolution of security for FPGAs. We also touched on safety and that allows me to bounce on functional safety. So functional safety is really defined as how do I ensure that my system keeps on running in presence of errors or even attacks, and that is best implemented when you essentially replicate the logic and use either a voting system or a majority system. So you have multiple instances of the same stuff running concurrently, and only if there's agreement or majority, then you can continue. And this is what FPGAs can do. Being massively parallel, you can duplicate, triplicate the processing that you need and ensure that it keeps on running in regardless what's happening, electromagnetic events, malicious attacks from hackers, and whatnot. Functional safety is best in class with FPGAs. And in fact, in Enclustra, we have quite unique expertise in functional safety, and we will announce a functional safety module in the near future. And these are unique capabilities that it's much harder to obtain with software or CPU or GPU-based compute. Then the energy element is that the performance per watt, because this is the metric that you're interested. This is the performance per watt is again best in class for FPGAs. It's a very efficient machine. And if you look at frames per second per watt, for example, for video inferencing or TOPS per watt, FPGAs again provide best in class. GPUs from NVIDIA will give you the absolute best performance, but at a cost of a lot of power. They can be tremendously useful in the cloud, much less in the urban scale development at the device level. David, I'm sure you agree with that, and you have more to say.
Yes, sir. Yes, sir. So I started my industry experience in the power industry in Texas, and we used to run 138 kV across the fields and the plains, and we thought that was always going to be enough, and it's not. It's still not. So the energy is so important. The FPGAs live at the device level in some cases, many cases, and they're more energy efficient there. And oftentimes they can live on solar powered banks. And I actually have a solar powered camera system doing intruder detection at my mother's house 500 miles away. And I connect with it with G4, and I'm writing algorithms to determine whether or not the garage door is just opened or open later, or trying to figure out she's at that age where we need to be careful with what's going on there. In terms of FPGAs, they also live, of course, at the edge, which is not necessarily at the device level, but that's where energy efficiency is so important. The NVIDIA CPU, GPU, that whole AI generative thing is based upon, redundant statistical analysis. And so they're going to run over and over and over and over and over and over and over again until you get the right engine that you can deploy that's not going to take that much. And I'm mind boggled, again, I don't use that word too much, as to how much energy is being used by our government in terms of just doing AI work. And why do they need that much, and what are they doing? I'd love to find out, but they won't tell me. I haven't really asked, but I don't think they will. So talking about protection against EMI, so being a ham radio operator for many years and having worked in the communications industry, it's important to have a local enclosure, an IP67 type enclosure that is going to shield EMI, not only from outside world, but from the inside getting out. We really don't want all of these devices out there oscillating at 452 megahertz, whatever they might be doing, and causing other EMI problems. So it's important to find a way to get them into containers, and one of the ways is to pop them, of course, but that's not always practical. But tamper-proof enclosures are important. So there's an entire another market there, another revenue stream that someone's going to take advantage of. The FPGAs at the DNS level, I think they provide some of the best firewalls you can have. I've seen a lot of the DNS traffic stopped because of bad actors and denial of service attacks, and FPGAs are involved, and I think it's a great thing.
Okay. Gael, was there anything else you wanted to add on this question?
Well, yes, but briefly, we touched on this, the reconfigurability. Obviously, we're all used to software flexibility, right? We can always fix or improve software and download it over the air in a secure manner, right? What FPGAs bring on top of that is hardware reconfigurability. the ability to expand the hardware perimeter, maybe to add new types of sensors without changing the processing logic, right? Maybe, I think, especially when you have so many proprietary formats in sensors technology, this is not a well-standardized industry. So the ability to reconfigure the hardware is extremely important. And I would say even more so for security elements, right? Because it really allows you to potentially significantly upgrade. An example would be moving from traditional encryption technology to post-quantum encryption technologies can be done as easily as a software upgrade, what looks like a software upgrade, but hardware upgrade in the FPGAs, and yet maintaining super high speed, real-time processing. A CPU typically would not be able to evolve into post-quantum era without changing the hardware. FPGAs can do that, which is really awesome. So you can always maintain and stay up above the level that you need, barely up what you need to be in order to provide the best trade-off between safety, security, and cost to the mix. So it's wonderful devices. They don't let you down, right? They remain your best friend for many years.
Very true.
Okay. Okay. So let's now move on to, let me ask you this. What are some practical first steps for someone looking to use FPGAs and AI? David?
Thank you. Well, stakeholders. The very first thing you always have to do in any endeavor is to talk to your stakeholders. And those aren't necessarily just the people who are writing the checks. Those are the people who are going to receive the services. And you need to make sure that those services can be delivered in a way that makes a lot of sense. Through Automation Doctor and some of the work that we've done, we've installed hundreds of machine vision systems. And actually, we're pleased to find out we're going to do a VSC webinar on that somewhere in January, I think. But I prefer to start with the interfaces. You need to find out what the customer requirements are. You make a traceability matrix, and you take those requirements, whether it be a resolution or a frame rate, or the distances that you have to telephoto, and then once you have the interfaces, once you have the requirements, then you figure out what your interface has to be to the device itself, right? Because obviously, to get data into the FPGA or the microcontroller or whatever you're using, you're going to have an interface that meets the standards that you're trying to achieve. With the new CSI ports that are on all these cameras now, CSI can only go 18 inches. It's not going to do anything for you. I mean, it's great for getting that data into that module, but at that point, you're going to have to talk to the other side of the edge. You're going to have to talk to the mid edge with something else. And so start with the camera interfaces, and there's almost no room for multiconductor cables. This means you're going to have to look at fiber, coax express, copper, Ethernet. Going to have to find ways to get the data to where it needs to go. And nothing happens if you can't do that. So that's the first spaghetti thread I like to pull. Wi-Fi is always possible, but traffic can be a problem. Plus, it may not be well known, but medical facilities, they do not want your Wi-Fi devices in there sucking down their bandwidth. They don't want all those images in the medical area going around. And when you have 9 or 10 cameras that are running in a medical device, they really want the other devices to run. That's more important, like the blood filter machine. It's more important. So I think the best way to start is to sum it all up is I like to find a moderate, proven, living design, and I know Enclustra has them. With a repository, a software repository that has all the project files that are required and that is ready to be built today in a specific integrated development environment. I like Visual Studio Code. People can use whatever they want. And that's not even touching on the software side of the FPGAs. But at the end of the day, you really have to have something that's ready to go. You don't want to spend 6 to 8 months dealing with libraries that don't work or trying to get this thing to interface with that thing. Everything needs to work when you first grab a hold of it. Now, there is a room for that R&D, and you should put certainly 30 to 40% more time into your project than you think you're going to need, because there are going to be things that need to be done. What say you, Mr. Gael?
Yes, well, I'm with you there. The first step would be decide what you need. Do I need a CPU or GPU and FPGA? And David, you really nailed it. As the amount of data, the connectivity requirements that you need is going to be your number one decision criteria. What's the plurality of data, sensing data that I need, and how fast do I need to process it? The second is going to be, what's my power budget? If you are in a low power budget, again, FPGAs are probably going to be your best friends. The third is going to be latency. I've mentioned that. If I really need low latency, again, FPGAs are going to be your best friends. If none of that apply, as I said, go for a CPU. That's the easiest and the simplest. Or a GPU if you need more compute. Once you've defined that you need an FPGA, the second layer of decision would be, what classes of FPGA do I need? And I see really three big clusters. We have the high-end guys, right? The AMDs and Alteras of the world with those completely integrated platforms that will deliver the best performance and leading-edge technology. We have our friends from Microchip who will deliver you the absolute lowest performance FPGAs, right? So if you're in the lowest power budget, then go look for Microchip solutions. They're really best in class. And if you are in the realm of ultra low cost, then we have our friends from Lattice Semiconductors and Efinix, just to name these two, which deliver extremely cost-efficient FPGAs. So you're well served with this industry, depending on your needs. The next step would be dev kits. All the FPGA vendors, offer cheap dev kits, which allow you to get started in minutes. For just a few $100, you can get a dev kit, lots of reference designs, lots of examples, and get started. Once you get to the next level, well, system and modules. Sorry for the shameless plug, but I would certainly recommend that you look at that. And Enclustra is the world leader, and we have those modules, and we have development kits as well, where those modules will plug into it. They're going to be a little more expensive than the very affordable dev kits from the FPGA vendors, but it will give you higher performance. You can actually develop a complete application on these, right? And lastly, the ecosystem. There's a ton of ecosystem partners to help you with AI models, with software tool flows, libraries for hardware functions or software functions, very rich ecosystem. So do not reinvent the wheel, right? Just focus on what you uniquely do different from competition.
Just as an added point on your dev kit, and that's a very great point I meant to touch on, but on your dev kit, make sure that your dev kit touches all the points of your traceability matrix. I have some horror stories that I can tell. I'm not naming names, but if you get something that runs in a particular language like Python and you want something else that runs in C++, and you want to put them together, they're not going to work in the same dev kit. In this particular case, it does, but then again, you have to figure out all of the translations yourself. It could be a mess. Just make sure your dev kit make sure it can touch all the points in your traceability matrix. That's all I'm saying.
That's a good one. And Linda, maybe I should also add, because FPGAs have a reputation to be much harder, and they are. But I would say, don't be afraid. If you get the guts to get on with that challenge, your product will be so much better than competition, right? Anybody can program CPUs. That's not that hard. But much fewer people can do it at the hardware level with those FPGA platforms. So go for it, because you're going to be rewarded immensely by being able to provide much better, much more efficient solutions than your competitors. Well, and there's a bunch of people like us to help you along the way. We even have design services to help you getting started if you so desire.
Okay. Anything else to add, David?
Just as a final question, I'm really excited. I've seen this industry since the early 80s, and I'm just so excited. I think by embracing the forward-looking approaches to our city's problems of sustainability and equity and resilience, and I think what's really important is the expandability that Gael talked about, and being able to reprogram the hardware that you have. I think the AI cities could usher in a new golden era of prosperity and happiness.
Yes, I could not agree more. And to me, Linda, it's really immensely rewarding to see that FPGAs can actually contribute to a better world. This is all what we're trying to do. And I'm not just talking about getting faster to my parking lot or getting faster to the office. Let me give you an example with waste management, right? In smart cities. A number of cities like Copenhagen and Madrid started to put sensors on either the buried containers or even the toters, the wheeled bins. And what they figured with that is collection was wrong in 75% of cases. In 50% of cases, collection was too late. And we've all been there, overflowing garbage in the streets, which is really not good. And in 25% of the cases, collection was too early, half full containers. Once they started to put down sensors, which can be weight sensors or visual sensors for a cardboard container, then they were able to reduce by 50% the collection of those garbages. And that turns out to be more cost efficient, but also it turns out it reduces pollution. Those big trucks that collect waste, they actually are quite polluting. So all of a sudden, smart technology like FPGAs can make it a better world, right? We have a better environment in our cities without the rats and the hygiene problems of overflowing garbage. And in the same time, we've reduced our footprint on the planet. And for me, this is very exciting to be part of this. I've been around FPGAs for so long, and it's part, my kids are very much into that, into being environmental friendly and respectful to our planet, and FPGAs can greatly help towards that. So I just wanted to share my excitement in those emerging use cases for FPGAs.
Well, thank you. I definitely hear excitement from both of you. I'd like to move on now to some of the questions that we have from our audience. A few of you, as I just mentioned, have already submitted questions, so we're going to jump right in. But as a reminder, if you would like to submit a question, type your question into the question window on the side of your screen and then hit the submit button. Okay, let's see what we got here. Okay, here's a question. How common are applications where you use inferencing of small LLMs in SoCs like Versal or Sync? And then it says, speaking of high energy consumption for modern AI, this would be a low power chatbot. So, Gael, you want to start with this one?
Yes. Well, so AI has been now ubiquitous in FPGA for quite some time already. And it starts with convolutional neural networks, CNNs, and FPGAs are extremely efficient at that. LLMs, so Gen AI, is also showing up in FPGAs, right? Although this is an emerging use cases, Gen AI is predominantly used in data centers type application, more for chatbot. And I'm not sure that FPGAs are necessarily the best platform for that. In smart cities, there's less today a use case for generative AI. I think it's coming up. And in fact, both Versal Gen 2, for example, support LLM type transformers as well as CNNs on their devices. Likewise, the infused AI capability from Altera allows developers to actually build the AI processing that is, fine-tuned to what the task that you want to do, whether you want to do a CNN or whether you want to do transformer-based, you can do it all in an FPGAs.
David?
I'm in agreement. So the large language models, and he's trying to do a chat box, it looks like, so he can have a box that will allow him to do translations in many languages into a large city where somebody can come up and put in their token or wave their hand or their phone or whatever, and they could allow them to converse with somebody else. Right now, I walk around with the Google phone in my hand, my iPhone in my hand, and with a Google Translator, I can try to go back and forth. But I love the idea of a chat box. But the large language models, I'm going to defer to Gael because I'm more in the convolutional neural network side right now and haven't done a whole lot with those, although they are high on my list, but they're not vision so much. And so being the vision guys, we haven't really scratched that surface as deeply as we should, but we are working on a project with a medical device company, and we want to have the languages, we want to have the conversation interpreted, and it's going to require different languages. So I think I'm on my way in that direction. Maybe Gael can help me out.
And maybe what I might add is what we're seeing as the trend is multimodal AI. combining CNNs and LLMs, that is transformers. FPGAs allow that. I'm also thinking of our friends at Hilo and CIMA, which also have dedicated silicon for that, which can be greatly combined with FPGAs to deliver those unique AI capabilities. So it's really happening, and the hardware configurability of FPGAs made them uniquely suited for AI. The pace of changes is extremely high, right? There's a new small revolution every other week or every other month, right? I think between two YOLO versions, it was as short as a month or two. So the ability to evolve my AI compute engine in hardware is unique. If I use dedicated silicon from NVIDIA, what I have is what I have, and I can't change it. With FPGAs, I can change my number format, my quantization, I can change my pruning, the size of my layers, how many layers I have. It's so adjustable. I love it.
Okay. Let's see. Here's another question. Have you got examples of smart city projects running, and do you see an ROI? We've talked about a few projects.
Yeah, I have that. I have an multiple example. Oslo in Europe has installed smart lighting system. I think it's over 65,000 LEDs. And what they've seen is 70% reduction in energy consumption. 70, which is enormous. And adaptive here will means that the lighting will be depending on what's needed, the time of the day, the natural lighting conditions, and even, I believe, only lighting up when there is something that needs to, if I'm walking down the street, it will only create a halo of light around me, and it's not going to light up the part of the street where there is absolutely nobody. So here, this is 70% reduction. In the waste management, I think it's University of Idaho in the US, who was able to reduce by 50%, so cut in half the cost to do the waste collection at the university. And there's many other examples where there is indeed a very, very tangible, significant ROI in cost of operations, in the environmental impact, energy consumption. It all goes in the same direction together. So there's an investment in the tech, which results simultaneously in better operating conditions, safer operating conditions, lower energy, and lower or improved impact on our planet. So not just money, by the way, all indirect forms of improvement.
It's interesting. David, do you have anything to add?
The only thing I would add to what Gael has said is that, and maybe embellish a little bit, is that return on investment is going to be so hard to measure, because how do you measure, satisfaction of your citizenry? How do you measure what you didn't do? All right. So if you are looking at traffic patterns and that traffic pattern made a shift on a particular day because of an event, or on a particular month because of the weather, and now we don't have as many wrecks, now we don't have as many things. We have things that didn't happen, and it's so difficult then to put a finger on what that saved us. But I'm very, very glad to see that it's happening that way.
You're so right, David. Traffic jams, I think, have an enormous cost to society. So reducing that alone is going to improve productivity, which is a very tangible ROI, probably in billions per year throughout the planet.
And you've spoken before about the climate enhancement that you can do by rerouting people so they don't sit in traffic and burn fuel, although a lot of our cars aren't doing that now. You still, if it's an electric car, you still got to charge it, and that still has a fossil footprint somewhere. So it's just important to make sure that we don't waste energy.
Mm-hmm. Mm-hmm. Yeah, absolutely. Okay, let's see here. I think we've got time for one more. Is the Versal FPGA the device of choice for AI-based applications? I'm
going to take that one. So this is one of them. As I mentioned today, on the AI side, if you look at the leading edge solution, you've got AMD Versal, as well as Altera Agilex. Both of those vendors give you exceptional AI capabilities with some differences, both of them exceptional, both of them as a complete platform that can do wonders to you with the IOs, the AI inferencing, and the SoC control system, all integrated. So for high-end AI, I would look for that. Now, you also can do extremely cost-efficient AI in microchip devices and FNX and lattice devices, lower performance but extremely low power. So depending on what you need. A great example that a lattice has demonstrated is the ability for systems to infer if the human operator is actually watching the device and only then interact. So for example, the screens will be turned off until you actually look at the screen. And then it will turn on, and that saves energy, but it's also great security features for industrial applications. So there's more than one device of choice here. And that's what's great with FPGAs. A lot of offerings from different vendors.
Very cool.
Yes. Yeah. Very fair.
I had a question for Gael about the software package that is used on their systems and how that's leveraged into the common user.
Well, thank you. And I touched already on it, but I can recap that. So it's essentially you have three tool flow when you're dealing with the FPGA. Remember, there's three compute engines, right? One is going to be your programmable logic tool flow to do all the sensor fusion and the parallel data processing. And that's the traditional tool flow. Second is going to be your SoC tool flow, which is really just a CPU tool flow because that's what it is. It's an embedded server, in a sense, into your FPGA platform where you can compile on those multi-core subsystem. The third is going to be your AI tool flow. And again, all these vendors, they give you great AI tool flow. The starting point is everybody wants to be able to ingest trained model that were not designed for FPGA. So the starting point is you take any trained model that you have or you can buy on the shelf or get on the shelf and, Hugging Face, for example. And then the tool flow from those vendors, FPGA vendors, will allow you to very quickly optimize down that network, those layers, in order to get great performance out of the silicon. They're very easy to use. And in a few number of iterations, you'll be able to quantify, use the number format that works out, choose the layer types, configure your inferencing engine so that quickly you get really high performance and power efficiency. Remember the key metric is performance per watt. So there's a complete tool flow available to all of you guys here to get started today with AI on FPGA platform.
How does VHDL and Verilog interface into that scenario?
Well, David, the HDL Verilog, this is the first part I mentioned. This is the sensor fusion part. This is traditionally how you would do that part. AI does not need any HDL coding at all. Today, when you want to do AI for Altera, Agilex, or AMD Versal, you do not need any hardware knowledge. It's all ready to go for you, and you really just need a model and a few optimizations of that model through the tool flow to get started. I should also mention, by the way, that even for HDL, there are HLS, high-level synthesis tools today that exist that allow you to design your sensor fusion part in C or C++. And that is a great way to actually get a working system really quickly. And potentially down the road, you can further optimize down, cost reduce that sensor fusion part using HDL or VHDL or Verilog. So it's very, very much a software-defined experience that you have today.
Mm-hmm.
Thank you for clearing that up for me. I'm all about the fast start in the
integration.
Okay.
No need to be an HDL expert.
Okay. Well, on that note, I'm afraid we've run out of time. For those questions we didn't have time to answer, we'll get back to you via email. This concludes today's presentation. On behalf of Vision Systems Design, I'd like to thank our speakers for their insightful discussions today, Enclustra for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of your day. Thank you.
Thanks, everyone. Have a great day.
Goodbye, friends.
Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.